I want a motion diagram. Not in detail. In other words, I want this, or I want this, or I want this. That's what I mean by motion diagram. Identify whether it's accelerated or not. The second thing here, there's this force identification diagram. And this is really sort of like to conceptualize free body diagrams. And you might, some people will say like, oh man, that's just a pain in the ass to do that. And I go like, yeah, I agree. But the bottom line comes down to this, is that if you cannot draw the right free body diagram, and by the way, there's a good 25% of you will not draw correct free body diagrams on exams and quizzes, and it hurts me, but I'm going to take off a shitload of points. You need to really nail this thing down. And then the third thing here is that then we draw a free body diagram, and this is a mathematical picture. That means you should be able to go from your picture should immediately then allow you to write out the N2L equations. These two guys are connected. And that's why the free body diagram is so important. If you get the free body diagram, you get the wrong equations. As far as I'm concerned, you've messed out on 3/4 of the problem. That's how important it is. Okay, let's go look at this thing here now. Okay, so let's look at the first one. So let's look at this here. So let's look at A. So A says you've kicked a rock on the sidewalk and it's now sliding along the concrete. So what do I mean by that? Well, I agree that we have the ground. And I have some rock, okay? Let's say this is the rock, right? And so you could imagine that you're going to come in with your foot and you're going to kick this thing. And when you kick this thing, for a moment in time, you are now applying a net force on this rock from your foot, right? Your foot is applying a force on this rock. So what is the picture that I see? So the key to this thing here is it is now sliding along the concrete. So here we go. I have the concrete. And now I have the rock that's now moving in this direction. In other words, it has some velocity in this direction. Does the rock continue to, okay, so the question is, in this picture, note, there's no foot anymore, right? The foot has stopped acting on the rock. So here we go. Question. Why does the rock continue to move forward after it got kicked? The answer is, of course, Newton's first law. It will continue to move forward forever. But it doesn't move forever. Right? But that's the reason why it's going forward. It's because of Newton's first law says that it's going to continue to move forever. But what you're finding here is that in this scenario here is that as the rock is going across here, what we do know is that there has to be what? Some type of deceleration. Right? As soon as we know that there is deceleration, now we know that we're in forced. So now the rock slides and slows down. That means it's in forced motion. If it's in forced motion, that implies something is causing this effect. I just saw RJ's question. The answer is yes. There is friction. And when I say the net force, it's the force of the foot minus the force of the static friction on the rock. But there's a net force. And remember what I said, I cannot tell the difference between the force of my foot and the force of friction. So I should be writing the net force. So now what happens here? So now what I want to do here is that I sort of like want to conceptualize this whole process here. So what I'm looking at here is that I'm doing something like this. So just to get a sense of what is going on, I imagine I have my surface. And then of course I have my rock. And then what I want to do here is that when I'm looking at this thing, I'm going to come in here and I'm going to try to isolate this rock. That means I'm going to put a dashed line and ask the question, within that dashed line, what are the forces acting on this system here? Well, for starters here, we know that we must have the force of gravity coming down, right? The force of gravity is pulling down on this thing right here, right? It's pushing it towards the thing. But why doesn't it go all the way down? Because in this scenario here, there has to be what? There has to be the force of the ground. The ground is pushing up, and the ground is what we call the normal force. But when I'm looking at this thing, we know that there's a velocity and we know that there's an acceleration in the opposite direction. So there has to be something slowing that thing down. And what we say here is that we conclude here that there has to be friction here. So when I'm thinking about a force identification, diagram, I'm thinking about something like this here. But that is not a free body diagram. A free body diagram does what? Not only does it isolates the rock, then we convert the rock into its center of mass point. So then I come over here and I just say, okay, I come in here and I go like, I need a vector diagram. So that point is my rock, right? That is my center of mass. So this guy here is now my rock. And then I don't draw any coordinate system yet. I draw my vectors first. And what I'm seeing here is that these vectors should have all their tails at the origin. So then I see here that Since the rock is not accelerating up and down, we know that it must be in static equilibrium. So that means that the force of the ground, the force of friction, the force of gravity, which is typically written as mg, and then I look at friction, and it looks like this. Once I draw my coordinate system like this, I then come in, now that I have my vectors like this, then I draw a coordinate system. In general, there's two reasons why you would draw a coordinate system like this. One, so you draw your coordinate system where one, motion occurs along one of the axes. That might be the most important one. And then two here is that you choose a coordinate system where most of the vectors lie along the coordinate axes. And so, okay, so that's what that tells us here. And so then I look at the direction of the velocity. The direction of the velocity is in this direction. So I come in here and I say, the direction of the velocity determines the plus sign. And then for the y, it doesn't really matter, but that is my free body diagram. This is what I'm looking for. And because we know that this thing is decelerating, we then ask the question, what is the net force? In this case, the net force is what? It's friction. But look at the direction of friction. It's in the negative direction. And so the net force is friction in opposite direction of velocity. So then I'm going to go in, and from my diagram, I'm going to write out my N2L equation. So now I want to write out the N2L equations directly from the free body diagram. So I'm going to bring that free body diagram down with me. Okay, I'm going to bring that guy down with me because this is the important point here. And look what I'm going to do. I'm going to pay attention to my signs. Okay, how do I pay attention to my signs? Here I go. So the forces in the x direction, the forces in the y direction. Are there any forces pointing to the right? The answer is no. There's zero. Now I look at the frictional force. Which direction is that pointed? In the negative direction. Now I look at the force in the y direction. The forces are positive in the up direction, so you could see that the normal is pointed in the positive direction, so I put in a positive sign for the normal. And when I look at the force of gravity, you could see that it's pointing in the negative direction, so I put a negative sign exactly the way it is. Now, is this thing accelerating? Yes, it's accelerating in which direction? In the x direction. So I write Mass times acceleration, because why? It's slowing down. What about the rock? Is it moving vertically? No, it's in static equilibrium. So therefore, I'd write a 0. This is in static equilibrium vertically. So what do I want from you? I want this. Ultimately, I want you to tell me if this thing is, look at its motion. From its motion, draw a identification diagram, then draw a free body diagram. From the free body diagram, then write down Newton's equations without solving them. That's what I want. And that's what the quiz is going to be. So what I want to do.
Is that what you want on the problem set number 5?
If it asks for that, then the answer is yes.
Okay.
Okay. So let's go to this next one. So now I did that pretty slow. I want to try to speed up here a little bit. So here's the next one, B. A styrofoam ball just been shot straight up. Air resistance is not neglectable. So that means I need to go in and I need to do what? I need to go write down the, do that whole process here. So let's go look at that thing. So the first thing I'm going to do here is that, here, let me, apparently, gosh, I have 2 screens, so I'm always searching for my damn mouse most of the time. I apologize for that. Here we go. Okay, here we go, B. So now what are we going to do here? So we know that I have a styrofoam ball. Right? Is shot straight up. So I imagine that here's the ground, right? And if I have the ground, what I'm doing here is that I'm going like, the ball has been shot. So here's my styrofoam ball. It's been shot. It's right there. So as it goes up, I know that if I can't ignore air resistance, that means that this thing is doing what? That the ball is colliding with air molecules. So you're getting collisions with air molecules. So that means if I'm getting collisions with air molecules, that means I must be what? Decelerating. Right? I must be decelerating. So now, here I go. I want to do some type of identification. So that means if it's doing this thing here, then I imagine that if that's the case here, then what's really acting on that ball? Well, we know that there has to be definitely the force of the air molecules that are pushing down on it, right? So we would expect here that here you're getting some type of drag from air molecules. That's what we mean by the collisions. But at the same time, we know that gravity is doing what? It's pulling it down. Even though it's moving in the upwards direction like this. So now that I got that, sort of like identified, then I have to do what? I have to draw my free body diagram. So here I go, free body diagram. So now I'm going to go to my free body diagram. I want the mathematical picture. I take that ball, I put it at the origin. Then I see that there's 2 forces acting on this thing. Well, I know that I have the force of gravity. And I know that there's a second force on this thing. Let's say it's the drag force. Are there any other forces acting on this? The answer is no. So then I set up a coordinate system that does what? I pick its motion to be along one of the axes, and that lines up most of the vectors in that direction. So then from here, I then write the N2L equations. So I pick my velocity to be positive. And note that the X doesn't matter because there's no X forces. So what I'm seeing here is that I'm seeing here this, that the forces in the X direction is 0, right? There's nothing there.
So I have a question.
Yes.
When you're identifying which forces are acting on it, is this as it's coming down or is this when it's still going up?
It says that it was shot straight up, so it's going up.
Right. So why is there no force going up, presumably from the gun or whatever shot this thing
Oh,
up?
because it's already left the gun.
Okay, so as of this moment, there is no gun force.
Because if I look at the question here, the styrofoam has been shot up, has just been shot straight up. So it sounds to me like they're talking about that it's outside of the gun. If it was in the gun, then it would be telling you that something is accelerating it in the gun.
Okay, I understand.
Okay, so in this case here, we already know that the acceleration is going like this. So then I go, what about the forces in the y direction? Well, note that both forces are negative. So you could see that mg is pointing in the negative direction, so I have to put that negative sign. And when you look at the drag, it's also pointed in the negative direction, so that has to be doing that. So then, because this is decelerating, that means this force is what's causing what? The deceleration here. So let's go back up over here. What was the net force causing with the rock situation, causing the rock to slow down? Right? What causes the rock to slow down? F net. But what's F net in this case? It's the frictional force. That's the net force. That's what's causing it to decelerate. What's causing this thing to decelerate? It's the drag force and gravity. So in this case here, this is the cause of the net. This is the cause of the acceleration. You know what? You got to be really careful here. Note that A here, this has no sign. It's the force that's going to determine the sign of the acceleration. So what's my N2L equation? This guy right here. That's what I'm looking for right there. Let's go to the next one now. Here's C. It says an elevator suspended by a single cable has just left the 10th floor and is speeding up as it descends towards the ground. Let's look at that. So what's my picture here? So what am I focusing on? The elevator. So you could imagine I have an elevator, right? Here's my elevator. Right? I have my elevator. And maybe we have somebody standing in the elevator, right? So here's our person. And it says that we have a single cable. So I imagine that this is the cable right here. Now let's read what it says carefully. It says that we have a single cable. It's left the 10th floor and is speeding up as it descends. So that means it has velocity in this direction and it has acceleration in that direction. So here I go. So now what do we expect to happen here? Well, what we expect to happen here is that picture-wise, we imagine that if I start to draw a diagram in this scenario here, I'm thinking, can I identify the forces here, right? I want to be able to identify the forces. Well, for starters here, if I look at the cable, so now I'm going to go after an identification. Just to make sure I don't miss anything. So the identification then tells me that here's my elevator. I do not care about what's happening on the inside. I only care about what's happening. So if this is the cable, clearly there has to be some force of a cable, right? So when I isolate my elevator here, this has to be the cable pulling this thing up. And then, of course, we could see that gravity has to be pulling down. Should we think about air resistance here? We could think about air resistance because if it's speeding up, we would have air resistance in this scenario here. So in this case here, we could come in here and we could just say, well, there's probably going to be a little bit of air resistance, right? So we're going to say that there's some drag coming in. So now that I have that, now I want to convert this into a free body diagram. So here we go. So what do I know? So now I'm going to go into a free body diagram. I take that whole elevator and I create a dot. Even though there's a person inside, I only create that dot. And then I say, what are the forces here? Well, if it's speeding up, then I know that the force of gravity is an unbalanced force, right? The force of gravity has to be unbalanced. That means that when I look at the force of the cable, and then I look at the length of the drag here, that the combination of the drag and the cable has to be smaller than the force of gravity here. So now that I see that here, I'm going to put in my coordinate system. Which direction am I moving? In this direction, that's positive. The acceleration, we already knew had to be in that direction because we already know that there's a net force in this direction. Why do we know there's a net force in that direction? Because it's accelerating in that direction. So then I have negative. Again, we don't have anything in the x direction. So what actually happens here? So then I'm going to go write my N2L equations. So what I'm seeing here is that what caused the acceleration? It's the net force. And how I figure that out is then I'm going to come in and I'm going to sum the forces in the y direction. So maybe I should write the x direction is 0 since there's nothing there. So if I look at this here, the only way I can accelerate is that what? Look at the direction of gravity. It's in the positive direction. So I'm going to write positive FG. Look at the direction of the cable. It's in the negative direction. Look at the direction of the drag. It's in the negative direction. So what causes this elevator to accelerate? This is the cause. It's not the force of gravity. It's not the force of the cable. It's not drag. It's force of gravity minus F of cable minus drag. That is the cause of the acceleration. And that's what Newton's second law tells us exactly. So if I continue with the second part of this question here, it says, what if the elevator is slowing down? If the elevator is slowing down, then we have roughly the same type of scenario here, right? In this scenario here, again, we have our elevator. So even though the elevator is slowing down, the acceleration has to be positive. So then we can then move, since we've already done this once, we could move this a little bit faster here. So you're seeing that you have all the same forces as before. But there's something different. The only way that elevator could be slowing down is if what? The net force is now pointed up. The only way the net force can be pointed up, like in this case over here, in the first case, the only way this could be true if the force of gravity was greater than the force of the cable, plus drag here. So it's now different here. And what you're seeing here is that the only way you can get that is if now, I'm going to change my picture here because I don't have enough space here. I'm going to say that this force of the cable now must be, and the air resistance must be bigger than the force of gravity. That's the only way that could happen here. The drag is going to be the same. In fact, it would be even slower if the car's slowing down. So again, look at how I picked this up. My velocity is what? That is still positive. But now I have deceleration. And if I have deceleration, you could see here that the net force must be upwards. So here we go. Again, sum of the forces is 0. What about in the y direction? So the forces look exactly the same. It's going to be what? It's going to be minus Fg minus F cable. Oops, I said minus. I should have said plus Fg minus drag. And then I have mass times acceleration. But in this case, you're going to find here that this is the net force again, but this is negative because F of cable and drag are bigger than the force of gravity. So what causes the elevator to slow down? Most people are going to say what? They're going to say, oh, it's the cable. And I'm going to say, no, that is not true. The cable is not responsible for slowing down the elevator. It's the net force is the force of gravity minus the cable minus drag. That is the net force. That is what's slowing down the elevator. So here we go. That's my N2L equation. And the big difference here is that in this case here, this acceleration is positive, this acceleration is negative because the net force is negative. So let's go look at this next one here. This next one is slippery. So let's go read this guy here. So what you're seeing here is that in this scenario here, what do we have? It says a bag of groceries is on the seat of your car as you stop for a stoplight. Okay, so how do I do this? So what I'm going to do here is that I'm going to draw a slightly different picture here. Okay, I'm going to draw a slightly different picture. Let's say that I put those bag of groceries not on your car seat, but on the back of a truck. And I think the reason why is just going to be easier to draw so that you can actually see it. So I'm going to change this slightly. So here I go. So what do I have? I have a truck, right? And what you're seeing in this scenario here is that I have a truck with the bed. Right? And let's say you're driving a red pickup truck. And what we know here is that this red pickup truck is slowing down. So we know that it's decelerating. We already know that there's a net force that has to be going in the opposite direction. So now, here's my bag. Right? This guy right there is the bag. Now, what do I know? Question is, where's the observer? Okay? Where's the observer? If you're this observer, where you're literally at rest on the ground here, then we know that this is a good observer to apply N2L. It's an inertial observer. It's on the ground. Now, if I had an observer right here, let me move this down a little bit. Apparently I don't know how to do space yet. So if I have an observer on the truck like this is a non-inertial observer. And that tells me not good for N2L. And remember why I said that. The reason why I said that here is that, remember, if you're in your car and you apply the brakes, there is no cause to why your body moves forward, right? There is no way for you to say that there's a force being applied for you to make you go forward. So that's what I mean by a good versus a bad observer. So in this case, we know that this person is going to stop at this stop sign right here. And there's this deceleration. So I'm assuming here that if we're now talking about only good observers, we don't care about the non-inertial observer. We want the inertial observer. What we're seeing here is that the observer on the ground sees that the bag does not slide. So if it doesn't slide, what does this person conclude? Well, if I look at this thing here, so what do we see here? Well, we have the surface of the truck, right? Maybe we should do this here. We have the surface of the truck, and here's the surface of the truck bed. Let's call this the truck bed. And because of the bag, right? Here's the bag right here. What we're seeing here is that we know that the force of the truck is doing what? The bed of the truck the truck bed has to be pushing up forward. And then, of course, we know that we have the force of gravity pushing down, pushing it down. So the question is, that tells us why the bag isn't moving vertically, but why isn't this thing sliding if it's moving with that kind of velocity? So in the frame here, what we're seeing here is that there must be what? There must be an additional force of friction. So what's causing? So the question is this bag is slowing down. There has to be a net force that's slowing it down. So in this case, what we're seeing here is that it's the force of friction that's actually doing that. So now let's go draw the free body diagram. And if I draw the free body diagram, it looks like this here. So now my free body diagram is a mathematical picture. There's a point, and I could see here that because the normal of the bed and the force of gravity are equal and opposite, their forces must be balanced out. The force of friction is the only unbalanced force. So when I start to then go in and put my directions here, a good choice of directions would be something like this. So now, here I go. The force is in the x direction. There's only one force, and it's pointed in the negative direction. It's this force that's doing what? This is the cause of the deceleration of the bag. And then I come in and I apply my forces in the vertical direction, and then I see the normal's pointing up, the force of gravity is pointing down, and the fact that this thing is in equilibrium, that tells us that it's in static equilibrium because it's not moving. So Newton's second law tells us that that's what we have right here. That's our picture. It would be static friction because it's not moving. If it was sliding, then we would have kinetic friction that's doing that.
And there's no force going in the positive x direction because I guess I'm wondering in terms of the fact that it has the velocity of the truck, but you're saying there's nothing that's causing it. There's nothing that's pushing it to have like that. There's no force with that.
No, there isn't. And the reason why that is the same reason with the rock. Once you kick the rock, why does the rock continue to move forward? It's because of Newton's first law. Why does the bag continue to move at constant velocity? Because it's under Newton's first law. No force is required to keep it in that state. So that bag continues to move forever unless something is forcing it to slow down. What's forcing the bag to slow down? It's the force of friction.
Got it. Thank you.
Okay, so remember that guy, the green guy, the observer on the truck, right? The observer on the truck, God, man, this mouse is killing me today. That green observer, he can't apply Newton's laws because he sees no force acting on the bag. He does not understand why there's no friction because he's at rest with the bed truck. He's at rest with the bag, which is kind of out there if you think about it.
Well, what about the force of inertia?
There is no force of inertia. What's the agent that causes force of inertia? Right? And by the way, that's a very common statement. That is a really common statement. And the other one that people use is the force of momentum. There is no force of momentum. There is no force of inertia. It's Newton's first law that you're really trying to say. Objects want to continue moving at a constant velocity forever. That is not a force. So the fact that it's continuing to move forward is Newton's first law. But the fact in this case here, it doesn't continue to move forward under Newton's first law because now it's being forced to decelerate here. By the way, I think that's a really hard concept.